Hello, I'm Saritha Kumari, Assistant Professor, EEE Department, working in IARE, Hyderabad. Today, I'm going to explain about RMS value of an AC signal and problems based on that, then form factor and peak factor and concept of impedance and admittance. So, RMS value of AC signal. So, in my last lecture, I have explained about the average value of AC signal, how to calculate the average value. So, the next one is RMS value for the AC signal. How to calculate? There are two values for an AC signal. So, now I am going to explain about the RMS value of AC signal. That means a periodic wave. So, here RMS value means root mean square value. While calculating root mean square value of alternating quantity, it is nothing but heat energy produced by the constant voltage, DC voltage. The RMS value of AC is nothing but heat energy produced by constant voltage. Now, this RMS value of an AC voltage is defined as, that constant voltage will produce the same amount of heat energy as produced by AC voltage when both are applied to same circuit for the same period. See that this RMS value is defined as that constant voltage which produces same amount of heat energy produced by AC when both apply to the same circuit for the same period. Now, the RMS value of AC is considerable importance in practice because the ammeters and voltmeters record this RMS value only when they connected in the AC circuit, right? So that is important. The RMS value, it is important because in the AC circuit, the ammeters, voltmeters, AC ammeters, voltmeters connected, they record this RMS values only. So that is the importance of RMS value, root mean square value of AC signal. Now, to calculate this RMS value, again, like average value, there are two methods. First one is mid-ordinate method. So here, mid-ordinate method, as we already know, under average value, we know how to calculate it. It is calculated graphically. So, take an AC signal, okay, taken a waveform, here it is shown in the picture here. So, it is divided into n equal parts with the instantaneous voltages during the equal intervals T1, T2 and so on Tn. Corresponding instantaneous voltages are V1, V2 and so on Vn. Now, see that. So, we can see the waveform. So, here it is divided into parts. Here, of course, n parts are not shown. Here we can see starting from 1 V1 to V12, V1, V2 and so on V12 with equal intervals. So, here let us say that is unequal intervals. Okay, here it is shown for a half cycle. So, on x-axis time, on y-axis voltage. Now, see that the RMS value of the voltage in figure. Okay, it is given in this mid-ordinate method. Expression is given by V RMS equal to square root. Okay, square root V1 square plus V2 square plus and so on Vn square over n under root. Okay, sum of the squares of the all the instantaneous values over total parts. Okay, under root. So that is a RMS value. In mid-ordinate method, how they calculate the RMS value. Next, second method, analytical method. So to calculate the RMS value in analytical method, the function is given by, see that here, this is a expression, important expression to remember, okay, to calculate the RMS value, whatever may be the function to calculate the RMS value. So here see that for a periodic function f of t, small f of t, with a period given capital T, the RMS value is given by f RMS equal to, its RMS value is given by, because the function is small f of t, so its RMS value is denoted with capital F RMS, suffix RMS, equal to under root. Okay, so in the name itself it is root means square value, so there is a square root, so under that square of the function. So remember like that, it is simple. So under root, okay, 1 by t given period, integral of lower limit is 0, because it is given only period is capital T. So initial time is not given, so take the lower limit is 0 and the upper limit is whatever the period given, capital T, that is, and square of the function f of t, that is f of t whole square dt. So that is a expression to calculate the RMS value in analytical method. Next, calculate this RMS value for a sinusoidal voltage. So here see that sinusoidal voltage means, we know that voltage expression is given by small e equal to Em into sine theta. Now RMS value over complete cycle. So for a full cycle, complete cycle, we calculate. So that is given by ERMS equal to okay, under root 1 by complete cycle means 2 pi. Complete cycle means that is nothing but 2 pi, right? So this is a cycle. So 1 by time complete cycle means 2 pi, 1 by 2 pi integral of lower limit 0 and upper limit 2 pi, and function is Em sine theta whole square, okay, d theta. Now solve it and see what is the value. So okay, I expand this, 1 by 2 pi 0 to 2 pi Em square sine square theta d theta. Get this Em square out of integration. So 0 to 2 pi. So sine square theta. So multiply and divide with 2. So it gives Em square by 4 pi. Okay, this 2 is out of the integration. So it is 2 sine square theta. So we know that from the basic mathematical equations, standard equations, 2 sine square theta is written as, in terms of cos 2 theta, as 1 minus cos 2 theta d theta. So Em square by 4 5, get out of the root, that becomes Cm by 2. So 0 to 2 pi. Okay, so I'm simplifying. Integral of 1 is theta, sine, cos is sine 2 theta by 2. So 2 pi. Now simplify, Em by 2 under root 1 by pi 2 pi, and sine 4 pi is 0. Okay, so 5 pi gets cancelled. So here we can get Em by root 2. So Em by 2 into root 2 means Em by root 2. So that is a expression that is a RMS value, that is RMS value of sinusoidal signal. Okay, so for a voltage signal, that is given by ERMS equal to EM by root 2. If it is a current signal, current, then what is a equation of that current signal? I is equal to Im sin theta. Then for this current, then if we solve for complete cycle, the RMS value expression will be similar. Okay, expression, that is Im by root 2. So that is how the RMS value of a sinusoidal signal is calculated. Next, based on this, we have small definitions, that is form factor and peak factor. Form factor is defined as it is a ratio of RMS value to the average value of the wave. Whatever may be the wave, okay, it is defined as form factor, ratio of RMS value to average value. So that is why it is given as in a ratio, form factor is equal to V RMS by V average. If we calculate this form factor for a sinusoidal signal, because we know what is a VRMS expression and V average expression. So for a sinusoidal signal, this form factor value is given by, okay, VRMS is, we know that, Vm by root 2. VRMS is equal to Vm by root 2. And its average value equal to 2 Vm by pi. So if we simplify, if we calculate the value, its value is given by this 2 by pi, 0.67 Vm, and this 1 by root 2 gives 0.707 Vm. So substituted here the RMS value and average value, the form factor for a sinusoidal signal is given by 1.11. Then peak factor. Peak factor is also called crest factor. It is defined as the ratio of maximum value or peak value. Okay, ratio of peak value to the RMS value. Ratio of peak value to RMS value of the wave. Now that is expression, mathematically it is written as peak factor equal to Vm by V RMS. So for a sinusoidal signal, again calculate this value, peak factor value, that is given by, okay, Vm by VRMS means 0.707 Vm, that gives Vm gets cancelled, this value gives 1.414. So that is about the form factor and peak factor. Now next we have small example problems for better understanding of this basics of the AC signal. So see that here, first one, the period of a sine wave is 20 milliseconds. What is the frequency? Okay, the period of a sine wave is 20 milliseconds. What is the frequency? So here if we see, they have given the time period, that is capital T, we know that denoted with capital T. Period or time period, it's the same. Okay, so for an AC signal, period means time period. Its value, it is denoted with capital T and its value is given as 20 milliseconds. And its frequency, what is the frequency? We know that the relation between frequency and time period. So frequency is given by 1 over time period. So 1 by 20 into 20 into milliseconds means 10 into 10 power minus 3. So it gives, okay, it gives 50. It gives, okay, after simplifying this we get 50 units of frequency are hertz. Already, okay, we know that. Now next small example problem. The frequency of a sine wave is 30 Hz. what is the period? The frequency is given 30 hertz and what is the period? So here given frequency is given and they're asking the period. So by knowing the relation between period and frequency, that is uh, they are inversely proportional to each other. So period is equal to time period t equal to 1 by frequency. So that is 1 by given is 30. So substitute, we get 0.033. So which gives 0.033 seconds. Now convert that simplified, it is written as in milliseconds, 33.3 milliseconds. Next problem. Okay, a sine wave has a frequency of 50 kilohertz. How many cycles does it complete in 20 milliseconds? Given sine wave frequency, 50 kilohertz. Now they are asking how many cycles does it complete in 20 milliseconds? Okay, in that particular 20 milliseconds, they want to know how many cycles it completes. So, as we know already, using the relation between frequency and time period. So, number of cycles means we know that from the definition of frequency. It is defined as number of cycles, time taken to complete number of cycles in 1 second, right? So here frequency, that means cycles, number of cycles, that is nothing but frequency equal to 1 by t, that is given, they asked in 20 milliseconds period. So 21 by 20 into 10 power minus 3. So it gives 50. It gives 50 cycles per second or hertz simply. Now next problem. A wire is carrying a direct current of 20 amperes and a sinusoidal alternating current of peak value 20 milliamperes, and find the RMS value of the resultant current in the wire. Okay, they have given in a wire direct current is 20 and a sinusoidal current peak value 20 amperes. Now find the RMS value of the resultant current. RMS value of the resultant current. So that means we know that RMS value, how can we calculate? That is nothing but under root, right? Under root and square of the currents. So here direct current, because there are two currents, one is direct current, so under root, DC current square plus, and AC current, how can we take AC current? So we know that RMS value of AC current is nothing but Vm by Im by root 2. So that's why that Im by root 2 whole square. Im by root 2 whole square is taken. So substitute the values, 20, IDC 20 and Im also 20. So substituted and calculated, so it gives the total resultant RMS value, RMS value of the resultant current. Now, so look at this problem. It is a small problem, but important problem also. But important problem, because see that it's the problem is asking to calculate the average value and RMS values, of the given signal. So here see that a sine wave has a peak value of 25 volts. Determine the following values. First one, A bit RMS value, B bit peak to peak value, and C bit average value. Now, first, writing the given data, given peak value, that is nothing but peak value is denoted with Vm, right? So, 25 volts means given signal is voltage signal. So, peak value is a peak value of voltage signal denoted with Vm or Em, right? Is equal to 25. Then first A bit. So, we know that for a sinusoidal signal, the RMS value is given by in terms of Vm, that is Vrms equal to Vm by root 2. that is nothing but 0.707 Vm. Substitute Vm value 25, we get 17.67 volts. Next, B bit, peak to peak value. We know that peak to peak means, okay, from the positive peak to negative peak. That is nothing but that is given by 2 Vm or 2 Em. So, peak to peak value is 2 Vm, substituted 25 given data, Vm value. So, 2 into 25, 50 volts. Next, C bit, average value, that is V average. So, that is given, we have the expression in terms of again peak value 2 Vm by pi. So, 2 Vm by pi means 0.637 Vm. So, that gives substitute for Vm 15.9 volts. Next topic we have is reactance, impedance and admittance. Okay. Concept of reactance, impedance and admittance. Okay. See that? So in case of AC circuit, okay, in AC circuit, okay, we come across this, okay, we come across this new terms, okay. So now see that. So in the starting of AC circuit, okay, already we know this point, okay. So in the last class, in the last lecture, so in the last lecture, okay, so first thing under AC circuit I mentioned this point, okay. So same thing here, it is repeated, okay. In electric and electronic system, look at the first point here. In electric and electronic systems, reactance is a opposition of a circuit element to an AC signal, that is AC current or voltage, okay, due to the element inductance or capacitance, okay. So here in AC circuit, okay, the reactance is there, okay, because of the inductance and capacitance are any one of them, okay. So reactance is the opposition of circuit element to AC signal. Now reactance, okay. So reactance is measured in ohms, okay, like resistance only. Units are same, ohms, but it is denoted with symbol X, capital X, denoted with symbol capital X, okay, to distinguish it from a purely resistive R value, okay. Now in case of an inductor, the reactance of inductor is called inductive reactance. It is denoted with symbol XL, X suffix L, and it is measured in ohms, okay. Units are same, ohms only, but only the thing is, point to be noted is, if the element is an inductor, then the reactance is called inductive reactance. It is denoted with XL, okay, it is denoted with XL and units are ohms. Now, if it is a capacitor, if the element is a capacitor, the reactance of the capacitor is called capacitive reactance, denoted with letter symbol XC, and it is measured in again ohms. Measured in ohms. Now, see that. So now we know what is a reactance. Okay, it is a opposition offered to the opposition of circuit element to the AC signal due to the element inductance or capacitance. Now, after knowing this reactance, okay, what is an impedance? Okay, we next come to impedance. Now, impedance, okay, it is defined as impedance, okay, it is defined as the ratio of sinusoidal voltage to sinusoidal current. Okay, like resistance. Okay, resistance, how it is defined? Okay, it is opposition to the flow of current. Another way we can say from Ohm's law. From Ohm's law, resistance is given by ratio of voltage to current. Okay, in the similar manner, this impedance is defined as ratio of sinusoidal voltage to sinusoidal current. AC voltage to AC current. Okay, so that means in place of resistance, okay, we have this impedance. Okay, because it is a AC circuit. That is the only difference. Now, the impedance is, it is also defined as, okay, impedance is also defined as, okay, here know that impedance is denoted with letter Z. So, ratio of sinusoidal voltage to sinusoidal current, which are denoted with small letters. Okay, impedance denoted with the letter Z. Now, it is also defined as total opposition offered to the flow of sinusoidal current. Right, already we know this. Okay, it is also defined like this. So, the total opposition offered to the flow of sinusoidal current. Now, the impedance is measured in ohms. Okay, impedance is measured in ohms, like resistance and reactance. The units, okay, the units are ohms. Now, see that what is this impedance consist of? The real part of the impedance is resistance and the imaginary part is reactance. The real part of impedance is resistance, imaginary part is. That means know that this impedance has two parts. One is real part, another one is imaginary part. One is real part, another one is imaginary part. Okay, now they are telling what is a real part. Real part is resistance and imaginary part is reactance. So I write here in place of real part R and imaginary part I write X. Okay, that may be XL or XC. That may be XL or XC. Okay, now see that what is this J? See that this is an operator. Generally, it is used in electric and electronic circuits. Okay, to represent the quantities. Okay, to rotate by 90 degrees. Okay, this J is an operator. It is generally used in electric and electronic circuit to rotate the parameters by 90 degrees. It is an operator. Okay. Now, see that if we draw, okay, if we represent this real part and the imaginary parts, okay, this is how it is shown. See that on x-axis real part is shown and on y-axis imaginary part is shown. It is taken. Okay, so see that to show the impedance, okay, how the real part and imaginary part components are represented on graph. Okay, so they are represented graphically like this: real part on x-axis, imaginary part on y-axis. So see that what is a real part. On real part already we know that real part of the impedance is resistance. So on this, okay, x-axis resistance is shown and on the imaginary part is reactance. So we have taken imaginary part on y-axis. So on imaginary part reactance is shown. Now what is the resultant of these R and X? Okay, so the sum of, okay, so the resultant of this R and X. So we say this is a vector sum or phasor sum, right? So that is given by Z. Okay, this Z has magnitude as well as the angle. Okay, this impedance has, okay, both magnitude, okay, that is this length gives the magnitude and the angle, okay, and the other one, it has, along with the magnitude, it has the angle also, which is calculated here, okay. So see that. Now continuation, the impedance for series connected resistance and inductance. So see that, what is the impedance value for series connected resistance and inductance? Means circuit, in circuit R and L, right? So now, what is the impedance, okay, for this circuit? So what is the impedance? We know that, okay, it is given by, it has real part and imaginary part. Here real part is resistance, imaginary part is reactance, that is inductive reactance, especially because here resistance and the circuit has resistance and inductance. Now to calculate, that is what it is mentioned, it is shown here, Z is equal to R plus JXL. Now what is the magnitude, okay, for this? There is a magnitude and angle. So as I previously mentioned, okay, so here for this RL circuit, the magnitude is given by square root, okay, R square plus XL square, and the angle is, okay, angle is tan inverse of XL by R. Magnitude R square plus XL square, and the angle is tan inverse of, okay, tan theta. Calculate tan theta here. So what is this part? X. Here XL. XL by R. So that is for series connected RL circuit. Series connected resistance and inductance. Now impedance for series connected resistance and capacitance. Series connected resistance and capacitance, right? So what is a Z? Okay, usually, okay, this is how the circuit, then the total Z is given by, here see that the Z is given by R minus JX. For a capacitor, with respect to a capacitor, okay, J is taken with negative sign. So that is one difference, okay, when writing the impedance for a RL circuit and RC circuit. So know that for RC circuit, J is taken with negative sign. So that's why this Z is equal to R minus JXC. Okay, X in place of X, XC we have, and J is minus. Okay, now see that here minus J means, as I mentioned previously, J is an operator, right, which represent the quantities rotation by 90 degrees. Okay, so minus J means it is in anti-clockwise direction, okay, showing 90 degrees rotation in anti-clockwise. In previous case, plus J means it shows the 90 degrees rotation by in clockwise direction. Now writing the for RC circuit, writing the magnitude and angle. Magnitude and angle. So magnitude is square root, okay, square root of this under root square of the two terms, R square plus XC square, and angle is given by, what is the angle? Tan inverse of imaginary part by real part. What is the imaginary part here? Minus XC, okay, minus XC by R. That means negative angle we get for RC circuit. Okay, so that is how it is. Impedance is for a series connected RL circuit and RC circuit. Now let us say for RLC circuit, series connected RLC circuit. So RLC circuit, total Z is, what is the Z? Okay, real part is resistance and imaginary part is reactance. Here we see two, okay, both elements L and C are present. So it is given by R plus J XL minus XC. Exactly to say XL difference of XC. Okay. So if XC is greater, it will be minus J. So I have to write plus or minus. So if XL is greater, it will be plus J. Okay. So this is how the impedance for a series connected RLC circuit. Series connected RLC circuit. Okay, one more point here I wanted to add. So in drawing the real part and imaginary parts graphically, so this real part is resistance and imaginary part is reactance. So for RL circuit it is plus J, so XL. It is shown like this, positive y-axis. If it is a RC circuit, C is minus JXC, right? So we have to take R here and X here on negative axis. Okay, this is XC. The resultant of these two gives Z. Okay, so for RC circuit, the impedance graphically it is shown like this. Okay, real part on x-axis and imaginary part, that is XC, on negative y-axis. Okay, negative y-axis. This is 0. So it becomes, its value is minus XC. Okay, this is how for RC circuit. If it is RLC circuit, both positive and negative are shown. XL is shown and also XC also shown. Now, one more point, continuation here under the same topic. So we have one next parameter is here admittance. We come across next is admittance. See that in a parallel circuit, they are talking about a parallel circuit. That means if the elements are connected in parallel, right? Okay, if the resistance, inductance and capacitance, okay, are connected in parallel, that is nothing but parallel circuit. RLC. So in a parallel circuit, see that the inverse of the parameters will be useful for analysis. Okay, so in a series circuit, impedance is fine. Writing the impedance using resistance and reactance. Okay, but in a parallel circuit, okay, the inverse of the parameters, that means 1 by R, 1 by XL, 1 by XC is useful, they are telling, okay, for analysis purpose to solve the circuit. So now, we come across a new word that is here defined as admittance. See, that is how it is defined. The inverse of impedance is admittance. Okay, simply admittance is nothing but the inverse of the impedance. Now, it is also defined as, okay, if we know the definition of impedance, we can give the definition for admittance in this manner also. It is also defined as a ratio of sinusoidal current to voltage. That means small I by small v. Okay, admittance equal to ratio of, okay, initially know that it is nothing but simply inverse of impedance, and it is also defined like this. ratio of sinusoidal current to sinusoidal voltage. Now, okay, so this admittance also, here know that admittance is denoted with the letter Y, capital Y, capital Y. Okay, now this admittance also has real part and imaginary part, because impedance, okay, has the real part and imaginary part. So this admittance also has real part and imaginary part. Okay, here see that written see here, first admittance denoted with letter Y, that is given by 1 by Z. And now, okay, 1 by Z means we know that 1 by R plus R minus Jx, right? That may be XL or XC. So, if it is XL plus Jx, if it is XC minus Jx, that's why it is mentioned like. Now, it is written as 1 by R plus R minus Jx, G plus R minus Jb. G plus R minus Jb. What is this G? What is this B? Okay, so this G is the real part here. See that? The real part of admittance. It is conductance. Okay, it is conductance. G. Okay, and imaginary part is susceptance. Imaginary part B. Okay, it is susceptance, denoted with letter B. Letter B. Now, what is G in terms of resistance? That is a real part, right? 1 by R. What is B? That is imaginary part, right? That means 1 by X. Okay. So this is about the admittance. This is about the admittance. Okay. So admittance is a inverse of impedance. Okay. Denoted with letter Y. Okay. And it has the real part and imaginary part. So 1 by R plus R minus Jx. So G plus R minus Jb. Okay, so this G is conductance, B is susceptance. Okay, so that is about the admittance. Okay, so that is about admittance of an AC signal. What is meant by an admittance of AC signal? That's all for now. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.